So far we have developed a understanding of what a Laplace transform is, a little bit of an understanding about what it does. They're used to help solve differential equations. We haven't really seen examples of how that's used yet, but we'll see a little bit of that today. And we have developed a running list of Laplace transforms of some common functions that we know. So I just copied and pasted this all from the 7.1 worksheet. So just you should already have this on 7.1, but I just copy and pasted it over here just for convenience. We might refer to it a couple times today. So we know the Laplace transform of of 1, of t to the n, sine, cosine, e to the something, hyperbolic sine, hyperbolic cosine, pronounce them sinh and cosh, whatever. And so today we're going to be talking about the inverse Laplace transform. So in order to use Laplace transforms when solving differential equations, we also need to know how to undo them. If we think back to what we did in 7.1 when we discussed how are we going to solve these differential equations using Laplace transforms, we start with the differential equation, we do a Laplace transform, then that takes us to some algebraic equation where we solve for the variable capital Y of S. And then capital Y of S is just the Laplace transform of our solution that we're looking for. So you just do the inverse Laplace transform to get back to that original solution. So we need to know how to undo these Laplace transforms. We need to know how to do the inverse Laplace transform. So if you know ahead of time that the Laplace transform of little f of t is equal to capital F of S, then the inverse Laplace transform just takes capital F of S to little f of t. All right, so capital F and little f. Capital F is the Laplace transform of little f, and so the inverse Laplace transform just literally just takes you back to where you started. So in particular, all right, so all of these things are just the Laplace transforms of those common functions in this table over here. And so the inverse Laplace transform of 1 over s is just equal to 1. The inverse Laplace transform of n factorial over s to the n plus 1 is equal to t to the n, and so on. So we can just really just more or less just copy that table over. So 1 over s minus a, that is equal to e to the at, because the Laplace transform of e to the at is equal to 1 over s minus a. Let's see, this one right here was just t to the n. K over s squared minus k squared was sinh of kt. This was cosh of kt. K over s squared plus k squared was just sine of kt. S over s squared plus k squared was cosine of kt. So if we have a variable in the numerator over s squared plus k squared, that's going to be cosine or hyperbolic cosine. And then if you have s squared plus k squared, then it's just cosine. And if it's s squared minus k squared, that's cosh. If you have a constant in the numerator, it's going to be sine or sinh, and then plus it's going to be sine, and minus is going to be sinh. All right. Conveniently, so we use the fact that the Laplace transform is linear a lot in our computations. Same thing works for inverse Laplace transforms. So the inverse Laplace transform of some constant alpha times capital F, and this should be of s, right? Because your Laplace transform's variable is going to be s plus a constant times some other Laplace transform, capital G of s. We can just split this up as alpha times the inverse Laplace transform of capital F of s plus beta times the inverse Laplace transform of capital G of S. So how can we use this? Well, so if you're just asked to find the inverse Laplace transform of something that's over in this table, you can really just apply the table. But quite often you'll get something a little bit funkier looking, and you'll need to figure out like how can I use this table to get me there. And a lot of that is you're going to end up using a lot of partial fractions when you do this. So 1 over s squared plus s minus 20. We would like to write this. We would like to write this as a linear combination of things from this table if we can. And so what we do is we start by factoring our denominator. This would be s plus 5 times s minus 4. And then split it up using partial fractions. So this will be a over s plus 5 plus b over s minus 4. Multiply through by s plus 4 over s plus 5 times s minus 4. You'll get 1 is equal to a times s minus 4 plus b times s plus 5. These are just typical partial fractions tricks. You could plug in s equals 4 and get that 1 is equal to a times 0 plus b times 4 plus 5, which is 9. So b would be equal to 1/9. And you could also plug in s equals negative 5 and get that 1 is equal to a times negative 9 plus b times 0. And so a would be equal to negative 1/9. So now we can go back over here and say that this inverse Laplace transform is equal to the inverse Laplace transform of a over s plus 5 plus b over s minus 4. And now we know what a is, we know what b is. So we could just write this as negative 1/9 times 1 over s plus 5 plus b, which is 1/9, times 1 over s minus 4. Okay. Okay, hold on. I am just double checking my work real quick. Oh, okay. I think I missed, wait, did I mess something up? Sorry, give me 1 second. I'm just trying to make sure that I have my signs correct. Okay, well, I can just double check that by actually just multiplying all this through. So this would be like, so this is like 1/9 times negative s minus 4 plus s plus 5 over s squared minus s minus 20. And so this would be negative s plus s plus 4 plus 5, which equals 9. Okay, so I think this is actually correct. All right. Sorry, I might just be being a little bit paranoid. There might be some algebra mistake here or something, but anyway, whatever. If you see any like algebraic mistakes or something like that, please just like post it in the comments, so that like your classmates would probably appreciate that too. Anyway, I think this is fine right now. So you can now use the fact that the inverse Laplace transform is linear to just split this up. So negative 1/9 times the inverse Laplace transform of 1 over s plus 5 plus 1/9 times the inverse Laplace of 1 over s minus 4. So this is negative 1 over 9 times. Now we can just refer to our inverse Laplace table. And so we see 1 over s minus a. So that like our a would be negative 5 in this case. This is like s minus negative 5. So this is e to the negative 5 t plus 1 over 9 times e to the positive 4 t. All right. And okay, yeah, this is matching what I had from before, so I'm at this point I'm pretty confident in this answer. All right, cool. Inverse Laplace transform of 4s minus 1 over s times s squared plus 4. So again, we're going to do partial fractions, where we split 4s minus 1 over s times s squared plus 4 up. Okay, so we haven't done a lot of partial fractions this semester where we have one of our terms doesn't factor, or if like, you know, one of our terms is like raised to some higher power. We haven't done a lot of those, so you should be familiar with how to handle those sort of things. But anyway, for this case, how we'll do it is we'll split this up as a over s plus something over s squared plus 4. And we can't do just like b over s squared plus 4 because in general it has to be just a polynomial of 1 degree lower than whatever is in your denominator. So this is like a degree 2 term, so we have to put our numerator will be like a degree 1 term, so it's linear. So we need to put bs plus c. Okay. Yeah, and so if this seems weird or unfamiliar to you, I would highly recommend kind of just going back to you know, just freshen up on like the ins and outs of partial fractions. But anyway, I'm just gonna kind of plow ahead. From here, once we get the setup, all we do is just sort of multiply through by everything. So we get 4s minus 1 is equal to a times s squared plus 4 plus bs plus c times s. And so I could, see, write this as a times s squared plus plus 4a plus bs squared plus cs. And now I could group my s squared terms together and then my s term, and then I'll have this this constant term right here. And so my terms that are attached to the s squared have to sum to 0 because there is a like 0 s squared on this side. So a plus b is equal to 0. C times s is equal to 4 times s, and so c is equal to 4. So that's just free. And then 4a is equal to negative 1. These are our constant terms. All right, so a is equal to negative 1/4. This tells us that a is equal to negative b, so b is equal to negative a, so b is equal to positive 1/4. All right, so this is equal to the inverse Laplace of this whole thing, but now we know what a and b are. So, okay, so a is negative 1/4. So negative 1/4 times the inverse Laplace of 1 over s plus, and I'll just go a little bit slower here. So the inverse Laplace of bs plus c, b is 1/4, and then c is 4. Okay, normally I wouldn't even write this step. I would just kind of jump to the next step because we're going to split this thing into 2 fractions. So this would be negative 1/4. Maybe I can just, instead of writing this over, I can actually just do this inverse Laplace transform, because 1 over s, what gives me 1 over s? Well, the inverse Laplace transform of 1 is equal to 1 over s. So this is just negative 1/4 times 1. All right, and then plus the inverse Laplace. Okay, this is s over s squared plus 4. So this is like 1/4 times s over s squared plus 4. So it's going to give me that first term, and then plus 4 over s squared plus 4. And I can pull out that 4. And get this. Okay, cool. So this is negative 1/4 plus 1/4. And then what gives me s for s squared plus 4? So s over s squared plus 4 looks kind of like this one because I have a plus in my denominator, and it's like s over s squared plus something. So s over s squared plus something, and this something is like our k squared. And so if k squared equals 4, then k equals 2. So this is cosine of kt, so cosine of 2t. Okay, and then what about this one right here? So inverse Laplace of 1 over s squared plus 4. All right, so is a constant over s squared plus 4. So that means that our k, again, is going to be 2 because we have s squared plus k squared. But our numerator is supposed to be a 2, right? But our numerator is a 1. And we want it to be k over s squared plus k squared, so it needs to be like 2 over s squared plus 2 squared. So inverse Laplace of 2 over s squared plus 2 squared. So we can deal with that by like, so if we want to have a 2 in there, we can take a 2 out of this 4 and bring it inside. So this is like 2 times 2 is 4, right? And we're just borrowing one of those factors. You could also think of this as, you know, if you multiply the inside by 2, then you have to divide the outside by 2 or multiply by a half. And now we're pretty much done. Because this is just 2 times sine of 2t. All right. Cool. Doing that very slowly. So I think you should probably try this one. So if you don't remember how to split this up with partial fractions, the way that we are going to do that would be s squared over s squared plus 25 equals, so I've seen a couple ways to do this one. The way I've seen it before and usually like to do is write it like this. I think that you could also just write it as like as plus b over s squared, just to deal with the s squared part. I think those are equivalent, but yeah, and then plus something over s squared plus 25, and then we'll do cs plus d for that. So that's your setup, and that should be equal to 1 over s squared plus s squared, or times s squared plus 25. So figure out what your a, your b, your c, your d are, and then split this up accordingly, and then use your inverse Laplace transform table to finish it out from there. All right, I'm just going to assume that everybody has paused the video and done the problem, and I'm just going to kind of keep rolling. All right. Okay, so this tells me that multiplying through by everything, that I'll get 1 is equal to as plus b times s squared plus 25 plus cs plus d times s squared and then I just need to multiply through. So as squared times as cubed plus 25 as plus b s squared plus 25b plus c s cubed plus d s squared. This all equals 1. All right, so s cubed terms here and here, s squared terms here and here, s terms just the 1, and constant term is just the 1. All right, so this tells us that a plus c, so there's no s cubed terms over here, there's no s squared terms over here, and there's no s terms over here. There's just the constant. So we do a plus c is equal to 0. We can say that our s squared terms are b plus d is equal to 0. I could say that 25a is equal to 0, and then 25b is equal to 1. So b is 1/25. A is 0. This would tell us that, plugging a equals 0 into here, that c is 0. And this tells us that d is equal to negative b, which would be negative 1/25. So now we have our a, b, c, and d. So the inverse Laplace of 1 over s squared times s squared plus 25 is equal to, let's see, all right, so a is 0, b is 1/25, so I get 1/25 times the inverse Laplace of 1 over s squared, just applying that to this term right here, or you could say this term up here, they're the same, and then plus cs plus d. C is 0, so it's really d over s squared plus 25. And d is negative 1/25, so minus 1/25 times the inverse Laplace of 1 over s squared plus 25. All right, we get 1/25 times something. What gives us 1 over s squared? All right, well, 1 over s squared, this would be like if n is equal to 1, that would give us our denominator is like s to the power of 2. So n is equal to 1, so 1 over s squared gives us just t squared. So 1/25 times t squared minus 1/25 times what? So this is going to be really similar to what we did with this thing right here. So we have like a constant over s squared plus k squared. So constant over s squared plus k squared. Oh, sorry, this one right here. Constant over s squared plus k squared. This is s over s squared plus k squared. So constant over that equals sine of kt. But we need to have like a 5 in here. So we need to like multiply and divide by 5. So if we multiply this by 5, then we need to divide by 5 out here. So we're dividing by another 5. And then this now would give us sine of 5t. Yeah. So minus 1 over 125 sine of 5t. And then here I have 1/25 t squared. So this would be our inverse Laplace of this guy. Okay, cool. So there's a lot of algebraic manipulation going on with all this stuff. The best way to kind of get a feel for all these things is really just practice, practice, practice. You're really just kind of looking for you're just like manipulating these equations to get what you want, like this like multiply and divide by 5 thing. Like we're trying to like put this thing in a specific form, and so we're really just using a lot of algebraic tricks to get there. And so just the more that you practice with these tricks, like the faster you're going to get with them, the better you are going to get at recognizing them. All right. We're also going to need to know how to apply Laplace transforms to derivatives. So let's take a function y of t, and we're going to say capital Y is the Laplace transform of little y. Then this theorem is just all about the Laplace transform of the derivatives of y. So y prime, y double prime, and nth derivative of y in general. So the Laplace transform of y prime is equal to s times y of s minus y of 0. Okay, I'll give you the formulas for these things in a minute, but first I want to at least justify this first one for you, just so you can see where these things are coming from. So the Laplace transform of y prime, by definition, it's equal to the integral from 0 to infinity of e to the negative st times y prime. I'm going to write y prime of t just to be more explicit, because y is a function of t. All right. Now the trick here is to just do integration by parts. So u is going to be equal to e to the negative st, which makes du equal to negative s e to the negative st. Our dv is going to be chosen to be just y prime. And v is just going to be the antiderivative of y prime, which is just y. I could put like some like t's here if I wanted to. It doesn't really matter. All right, so applying our formula, this will be uv and this is really like evaluated from 0 to infinity, right? And minus the integral of v du. V is y of t, du is negative s e to the negative st. Okay. So this term right here is really the limit as b goes to infinity of e to the negative s times b times y of b minus e to the, plugging in 0 now, y of 0. Over here, these negatives cancel out, and I can also like factor out this s. And then from here, taking a limit as b goes to infinity, this e to the negative sb is just going to go to 0. And so this whole term right here is just going to go to 0. And we're just left with this right here. E to the 0 is just 1, so it's really just negative y of 0. And then plus s of, well, this is just the Laplace transform of y. So Laplace transform of y, I could write like, this notation up here, or I could just say, well, that's just equal to the capital Y of s. And what do you know? We get literally exactly this thing over here, just, written slightly differently. All right. Now, if you were to have like a double prime for your y here, you would you could do this same thing, and you'd get something very similar, except you would end up having to do integration by parts twice or 3 times if it was y triple prime, or if it's nth derivative of y, you would do it n times. We are just going to apply these formulas. So if you do it for y double prime, you'll get s squared times y of s minus y of 0 times s minus y prime of 0. Okay. There's a pattern that starts happening here. So this capital Y of s is always going to show up in the first term. And if you're doing the nth derivative of y, it's going to be multiplied by s to the n. So s to the n times capital Y of s. And then you're just going to subtract a bunch of terms. So you're going to subtract y of 0 times, not s, but it's just going to be s to the 1 less than this, than your highest derivative, whatever. So to the n minus 1. Oh shoot, running out of, I did not give myself enough space. Shock and surprise. All right, that, we're not done. So we have y of 0 times s to the n minus 1, and then minus y prime of 0 times s to the n minus 2, and then it would be like minus y double prime of 0, s to the n minus 3, and you just keep going until you get the n minus 1th derivative of y evaluated at 0. And it's like, times s to the n minus n, or just s to the 0, which is 1. But yeah, this is your formula for that. All right. So we are going to use that in solving these differential equations using Laplace transforms. All right, so this is something that we've like already seen how to do back in previous chapters, but we are just going to see how to do something like this using Laplace transforms. All right, so again, the method that we are going to do, if I go back to the previous worksheet, so we start with a differential equation. We're looking for a solution y of t. You do a Laplace transform to the entire differential equation. We should get some algebraic equation where we solve for capital Y of s, and then once we solve for that, just do the inverse Laplace transform to that thing and get back to your original solution. So that's big picture what we're about to do. So I do the Laplace transform of y prime plus 6y. That should be equal to the Laplace transform of e to the 4t. I think I should be using square bracket or the curly brackets here, but whatever, it's not that important. Fine, I'll just do curly brackets. Okay. All right, Laplace transform of e to the 4t, just going to refer to the table. E to the 4t gives us 1 over s minus 4. The Laplace transform of y prime plus 6 times the Laplace transform of y. That's what we get over here. So I'm just splitting that up. If you're doing these things fast, then you don't really have to write this step like every single time that you do this sort of thing. I'm just sort of not skipping steps here, just being very explicit. All right, y double prime, or wait, sorry, this is just y prime. Laplace transform of y prime is just going to be this, s times y of s minus y of 0. And then plus 6 times the Laplace transform of y. What is the Laplace transform of y? That is literally just capital Y of s. That's just, you know, how we define the notation. That's just the notation. These are just different notation for the same thing. All right, cool. What do we do with this y of 0? Well, we are told what y of 0 is equal to. So a lot of times when we have like initial value problems, this y of 0 equals 2, we'll use this. There will be like a plus c that happens in the equation somewhere, and so you kind of like solve the differential equation, and then you like plug this in at the end, and then solve for c, blah, 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 and then you get your whole thing. Weirdly, with this method, this y of 0 equals 2, just like you use that in the beginning, and then you never really have to deal with it again. So this straight up just tells us that y of 0 is equal to 2. So just replace that with 2. Okay, this and this, I could just factor out a capital Y of s, and I get s plus 6 times capital Y of s minus 2 equals 1 over s minus 4. So s plus 6 times capital Y is equal to 1 over s minus 4 plus 2. Divide by s plus 6. And then our goal here is going to be to, well, we're going to take the inverse Laplace transform. So this is the Laplace transform of little y. So we do the inverse Laplace transform of this guy, and we can say that so y of t is just equal, which is just equal to the inverse Laplace transform of capital Y of s is going to be equal to the inverse Laplace transform of our right-hand side, which is 1 over s minus 4, s plus 6, plus 2 over s plus 6. And so now we want to take this right-hand side and then just split this up into a bunch of things that we know the inverse Laplace transform of. So we'll have to do partial fractions on this. So let's do that up here. So 1 over s minus 4, s plus 6 is equal to a over s minus 4 plus b over s plus 6. So 1 is equal to a times s plus 6 plus b times s minus 4. Okay, plug in s equals 4, and you get 1 is equal to a times 10 plus b times 0. So a is equal to 1/10. And then plugging in s equals -6, you get that 1 is equal to a times 0 plus b times -10. So b is -1/10. So coming back down here, this is equal to, so I can split this up as a over s minus 4 plus b over s plus 6, and then pull out our a and our b. So a is 1/10, and it's inverse Laplace of s over 4, or sorry, 1 over s minus 4, plus b times inverse Laplace of 1 over s plus 6, and then plus 2 times the inverse Laplace of 1 over s plus 6. All right. This is going to give us e to the 4t. So 1/10 e to the 4t. And then 1 over s plus 6 gives us e to the -6t. And then same thing over here, e to the -6t. You could have combined these two to start with. You could also, like, here combine those into a single fraction. This is like 1/10 e to the 4t plus like 1 and 9/10 or 19/10 e to the -6t, just to make it a little cleaner. But that's what you get. All right. All right. All right. I suggest that you try this last one, and then if you're able to get it, then you're doing great. All right, so I'll give you a hint. So when you do the Laplace transform to the left-hand side, you're going to have to do the Laplace transform of y double prime. So you're going to have to apply this formula right here. You could think of it using like this formula right here and then just apply n equals 2, or you could just do this thing right here. And then you'll do like the same sort of steps that sort of happened up here, where you solve for capital Y of s. So you get y of s is equal to like something. And then this, whatever this right-hand side is, just try to split it up using like partial fractions or whatever. And then just take the inverse Laplace transform of both sides. Inverse Laplace transform of this is going to give you little y, and then inverse Laplace transform of the right-hand side. Obviously, you'll get something different from this. You'll just need to like refer to like either this table or this table. They give you the same information, so whichever table you want to use is the same, whatever. And then just finish it out from there. All right. I am just going to go right ahead and do it because I'm just assuming that you're going to pause it and unpause whenever you're ready. All right. So the left-hand side, I'll do the Laplace transform of y double prime, which would be s squared times capital Y of s minus, see the formula, squared y of 0 times s, and then minus, should just be y prime of 0 by itself, right? Yeah. Okay. And then plus 9 times the Laplace transform of y. So Laplace transform of 9y is just 9 times the Laplace transform of little y, which is just that. And then the right-hand side, Laplace transform of e to the t, is 1 over s minus 1, because this is like e to the at, and a is equal to 1. So the Laplace transform of e to the 1t is 1 over s minus 1. All right. We are told that y of 0 equals 0 and y prime of 0 is equal to 0. So this is 0, this is 0. All that stuff just goes away. So it makes our lives a little easier. And our left-hand side becomes y of s times s squared plus 9. Our right-hand side is just 1 over s minus 1. So y of s equals 1 over s minus 1 times s squared plus 9. I want to do partial fractions. This is a over s minus 1 plus bs plus c over s squared plus 9. All right. So this gives me a times s squared plus 9 plus bs plus c times s minus 1. Okay, I could do some trickery. You could plug in s equals 1 and get 1 is equal to a times 1 plus 9, which is 10, plus b times 1 plus c times 0. If you plug s equals 1 into s minus 1, this whole right term just becomes 0. So then a is equal to 1/10. Let's see, is there anything more I could do? I probably didn't need to do that. Whatever. Probably shouldn't have done that. I'm doing it differently from the way that I did it earlier. I'm just gonna plug in s equals 0 and see if that gives me anything. I have no idea if this is gonna work or not. Okay. All right, that's gonna give me that 1 is equal to a, which is 1/10, times 9 plus b times 0 plus c times s minus 1. All right, does this work? I have no idea if this works. Okay, this will work. I don't think this is the way I probably should have done this. But whatever, it works. All right, so this is 9/10 minus c, and so 1/10 is equal to negative c. Oh, okay, so this works out fine. C is equal to negative 1/10. All right, so we have our a, we have our c, we just need to find b. And I guess we could just plug in anything else that we want at this point. So we could just plug in s equals 2, and we get 1 is equal to a, which is 1/10 times s squared plus 9, should be 13, plus, we don't know what b is, but we have b times s, 2b, plus c, negative 1/10, times s minus 1, which is 2 minus 1, which is 1. All right, so we get 13 over 10 plus 2b minus 1/10 equals 1. So this is 13/10 minus 1/10 is 12/10. So negative 2/10 is equal to 2b. So then b is equal to negative 1/10. All right, cool. Probably not the most efficient way to do this. I just kind of felt like doing something different. I don't know why I did, but I did. All right, I did not want. Okay, I don't want the list of Laplace transform is attached to this, but I do, whatever. All right, I'm just going to keep that work below and say that y of t is equal to the inverse Laplace of capital Y of s, which is equal to, now we have our a, b, our c. So a, what was a? A was a tenth, right? So 1/10 times 1 over s minus 1 plus b is negative a tenth times the inverse Laplace of s over s squared plus 9, and then plus c. C was also negative a tenth. It's inverse Laplace of 1 over s squared plus 9. All right, here's the point where I check my work, just make sure I'm doing good. That's negative a tenth, that's positive tenth. Okay, cool. So this all seems good. This checks out. All right. Inverse Laplace of 1 over s minus 1, which is just e to the 1t. S over s squared plus 9. I'm just going to refer to this table. S over s squared plus 9 looks like this thing right here. So the 9 is our k squared, so k is 3, so this is cosine of 3t. And then this is the part where we have to like multiply and divide by 3. Because if this was like 3 over s squared plus 9, then we would have k over s squared plus k squared, so with k equaling 3. So I multiply and I divide by 3 to keep this thing the same while just manipulating it to look like what I want it to be. So 1/10 e to the t minus 1/10 cosine 3t minus 1/30 sine of 3t would be our final answer. Okay, and yeah, so I'm gonna post the filled-in notes for this as well. The filled-in notes that I'm posting are just gonna be the ones that I did originally. So if you don't like this way of doing this, you could just like look at my other way of doing it. They're both perfectly fine. I think I don't know why I felt like doing this on this video, but I'm doing this in one take, so I'm not doing it again.